So ladies and gentlemen, welcome to this webinar. My name is André Orsesi. I'm from France, from CEREMA, and I'm very pleased today to assist in the moderation of this webinar in which we will talk about the behavior of long-span bridges in a context of climate change. So just some notes. This webinar is recorded, and it is also being streamed live in the IAPSE YouTube channel. And after the end of this webinar, it will be placed on the e-learning IAPSE website. So I will share my screen and say a few words about the association IAPSE, the International Association for Bridge and Structural Engineering. So it's kind of a unique association with over 2,500 members in 100 countries, covering, in fact, not only bridges, but all types of structures and structural materials, with the objective to exchange knowledge and advance the practice of structural engineering. Just to mention the publications of IAPSE, first of all, a journal, the Structural Engineering International Journal, that proposes a mix of articles from practice to scientific papers. Also, you have the IAPSE bulletins. You find the structural engineering documents that are specific to some topics, like you can see some examples below. And also you have some case studies that are developed. And you also have the conference proceedings after conference events. IAPSE is organized with several national groups, which is kind of a unique organization in which IAPSE has the national groups that help reaching the objective of the association. It can be organization of site visits, workshops, and conferences. And there are the task groups. The task groups are in fact linked to some technical commissions, and you see here the 6 topics covered in the technical commissions. And in these technical commissions, you have some task groups. So a task group is like a mini committee in which the members meet and define some objective that they have to reach in a certain period of time. It can be from 2 to 4 years, sometimes it's a little bit more. And there is a specific objective to reach. And after the end of the task group, maybe the task group dissolves and the people regroup to define new objectives and new deliverables. At IAPSE, there is a young engineer program initiative. So for the young professionals who attend to the webinar today, you can check the IAPSE website, and it is a very good opportunity to meet international experts and interact. So check the website, and this is, I mean, a very good opportunity to create a network and to share knowledge. Here you have a summary of the IAPSE activities. So I mentioned some of them early on. What is important to mention here is the IAPSE Awards at the end of this year in November, and also the 2 events, upcoming events, with the IAPSE Symposium in Istanbul that will start next week on the topic of long-span bridges. And you also have the IAPSE Congress in New Delhi in September, focusing on engineering for sustainable development. For the symposium next week, IAPSE is still accepting delegates. And for the Congress in September, the registration will open soon. So should it be webinars or conferences, these events are a great opportunity to meet various profiles of members, consulting industry from could they be clients, owners, contractors, or academics. And this is, yes, a big change. This is very valuable to have this chance to meet all these members and to create a big network of in this community of structural engineering. So we come to the task group 6.1. And in fact, this task group was created in 2017 with the objective to exchange on the effects of climate change on infrastructures. And the strategy in this task group was to focus on a certain number of case studies. And with that, we've merged more than 30 experts from 15 different countries, discussing on some case studies linked to these effects of climate change. So on the left, you see the list of members. So I'm chair of this task group with Professor Alan O'Connor from Ireland. And you see on the left, the list of members. And on the right, you see the presentation of the webinar today. And I would like to thank Dr. Teng Wu from the University of Buffalo in the US for having accepted to participate to this webinar. Dr. Teng Wu is member of Task Group 6.1. And just before we move to the presentation, I would like to mention that there will be 2 other webinars organized by our Task Group 6.1. One in June on the left, and it will be about the risk of tsunamis in a context of sea level rise. And another one in October will be dedicated to the effects of climate change on material deterioration. If you want to know more about the work of the Task Group 6.1, you can also have a look at 2 papers that were recently published, in which you will find more information about our work. And also you can check some previous IAPSE webinars that dealt with the structural engineering in this context of climate change. And 2 of them in particular were organized in last year in November. To finish, just to mention that we have a Q&A session at the end of the presentation. So in your Zoom control, you have a Q&A button. So if you have questions during the presentation, put them in the Q&A, and I will notify them at the end, and I will discuss these questions with Dr. Teng Wu. Also, I would like to thank the IAPSE staff for their support today, and in particular, Firat Cishak and Cheryl Cornelio for helping us in the good organization of this webinar today. So with that, I will stop sharing so that Teng, you can share your screen and proceed.
Thanks, Andrew, for the introduction.
And the floor is yours.
Can you see my screen?
Yes.
Okay, perfect. Okay, hello everyone. My name is Teng Wu, and I'm from University of Buffalo. Today is a great opportunity for me to be able to share some of our recent research on the bridges and climate change. So for the wind design of a bridge and in general, wind engineering community, and recently the performance-based wind design has been advanced over the last couple of years. So the analysis framework for the performance-based wind design has been tried by for tall buildings, but has not been tried for the long span bridges. But the essential idea is like this. So we first have the wind field, that's intensity measure, and then we need to get the aerodynamic force. And then we have the structural response, and then we have the all kind of damage due to the low cycle fatigue or larger excursion. And then we have a repair cost calculated, or the all kinds of business interruption and injury or loss of lives. So so the whole framework, I mean the flow chart posed some challenges for us to this window design. For example, the first is we need a more accurate window climate analysis. One important part is the extreme wind hazard and the change climate. And of course, we have to consider all kind of wind duration, non-stationarity of those kind of more accurate capture of the nature of wind. And then we need to consider nonlinear and transient structure aerodynamics from the linear to nonlinear bridge aerodynamics. And or we need to consider the aerodynamics modification because of a transient wind or non-stationary wind. And then we also need to consider the nonlinear dynamic analysis, either distributed structure nonlinearity, as most from the geometrical nonlinearity, and also concentrated structure nonlinearity, most of them from the materials nonlinearity.
Yeah, it seems that we lost Tang for a while. We'll wait a few minutes. Hi, Tang.
And sorry, it seems like
issues with the connection.
so when would you mind to remind me which part I stopped?
Yeah, I think you can just share again the screen, and I will indicate that to you.
Yeah.
So please move on again. No, above, around the, yes, I think when you were at the nonlinear and transient structural aerodynamics, you can just come back to this part.
Thank you. So once we have those wind load, and then we go proceed into do the structure analysis. Usually in the wind engineering, we not go to the nonlinear structure analysis domain. And but under the performance-based wind design framework, we may need to go to the nonlinear dynamic analysis, either from distributed structural nonlinearity or from the concentrated structural nonlinearity. And then once we have the response, then we need the fragility curve to give us like some damage this part, and also we need a consequence function to get the cost estimation and this part. So both this part, currently we are lack of data in the wind engineering community, and not like in the seismic engineering community, but we are getting there. Many researchers are trying to, do those related studies to get those data. So, and if our structure is not satisfied, then we probably need to do something like a shape optimization and or like a control to achieve the performance objective. So all those things can be nowadays can be used combine the computational fluid dynamics and the computational structure dynamics, let's say, and do the fluid structure interaction. It's okay for us to do that for a giant project. To do like several scenarios, but the performance-based wind design, the thing is that the philosophy is that at each stage and for each block we have uncertainty, so we need to do the uncertainty propagation. So for this kind of consideration, so maybe the safety CSD coupling is not that feasible at the current stage because computationally too expensive. So we may need some like tools to help us to facilitate the whole process. So today's seminar, we will use the one example is that the winter climate and the climate change, and then to do the analysis until we get the structural response, and then to see what's the impact of the climate change on our structural response, specifically focus on the flutter, because this is one of the most important concerns for long span bridge wind design. So the first question we need to ask is, do our climate change intensify the extreme wind storms? And then the second question we would like to answer is, what would be the bridge performance under the intensified wind storms? And then the third question we would like to try to answer is that can we efficiently produce an optimal design for bridge wind retrofitting? And then the last question we're trying to answer is that can we validate the simulated wind-induced nonlinear bridge behavior in the wind tunnel? So to focus on the first question first, the background is that IPCC kind of just issued the 5 scenario in the 6th assessment report. And each scenarios, and if we is represented the CO2 emission trajectory, and with this as input, and then our output could be like temperature, humidity, and other climate variables. Use the global circulation model. So assess the projected change for the, let's say, the temperature. And each SSP scenario would be has uncertainty. Plus, each scenario, we don't have uncertainty assigned to each scenario. But if we use the global separation model to do that, the resolution is not enough for us, especially for the engineering and design. So most of the time we coupled with the regional model. So regional climate model can help us to get a better resolution for the climate variables impact what we are interested in, the hazards. So for example, the hazards could be the wildfire, the extreme heat, and all those things. But here, what we are interested in the wind storms. So currently, the windstorm, the climate change impact on the non-repeated windstorms, actually the confidence is very low because of the lack of data and also the required resolution. But the confidence on the hurricane or tropical cyclones actually is relatively high. So in our study, we are focused on the climate change impact on the hurricane intensity and frequency. So to accurately assess the hurricane or tropical cyclone hazard risk and the changing climate, the following information is to be carefully examined. First, we need a occurrence probability to climate change emission scenario. That part we don't, and I don't know when we can get that part, and probably not. So we need to have some like a strategy to attack that part, especially if we want to get something like climate change effects and on the structure design. Because our structure design is based on the reliability or like a probabilistic analysis. And then each emission scenario, we have a conditional probability distribution function for the regional environmental facts. And that is based on the global and the regional climate model. And then conditional PDF for each hurricane hazards. So if we get a set of environmental factor. So based on this logic, and we developed a climate-dependent stochastic simulation framework for hurricane wind, rain, surge hazards. And we not only be able to consider the most famous SST, sea surface temperature, we can also consider other climate variables. For example, the wind shear, the convective instability, and all those kind of things. So here, and then once we get those like hazard, like the wind, and then we can do some like quantitative work assessment. So the way to get the wind surge rain hazards is use the hurricane tracking model, and we can get at each specific location, we can get the wind surge rate. But here we will focus on the wind field simulation. So as the whole idea is about the risk, is about the probabilistic sense. So we may need to run many times because for example, the environment factor given to us maybe is a distribution, right? And we need to run many times to get what's the wind speed increase. So which means we need to run many like wind field simulation scenarios. Obviously it's not that feasible if we use let's for example, we use the WRF, those mass scale model to directly give us those hazards information, because there's a too computational cost. So what we have to be working is we use the AI tools to help us to get the wind field. So the more specifically is the machine learning or deep learning. So we know the input would be those storm parameters, and the output would be our target as the wind speed at a specific location. And if we want to treat the machine learning as a black box, then that's it. We generate data, and then we get the input, we get the output data, we train the deep learning, the network, and that's it. And then we can use the for all kind of purpose. But there are several challenges to use the machine learning to get the wind field. One is the large number of high quality data to training the network is not available. Because as said, if you want to use the WRF to generate the data, actually it's very time consuming. The second part is that black box makes those deep learning not easy to reasonably interpret, and not easy to accurately to interpret or even extrapolate. And also our engineers, we don't like a black box. So to this end, we proposed the so-called knowledge enhanced deep learning. Essentially, we would like to kind of take advantage of the knowledge we accumulated in this field and integrate it into the machine learning pipeline. And of course, we need to design all kinds of algorithms to integrate the knowledge. But here, I will not go to the details. But just use the hurricane simulation as an example. Then the obvious knowledge we have is the governing equation, right? For the wind and in general fluid, I mean, it's governed by the Navier-Stokes equation. And we can first do some simplification, and then we have the momentum and mass conservation, and then we can build those so-called knowledge enhanced deeper network architecture. If you say examine the architecture of this network, we have the input, we have the output, but compared to the conventional black box, and we have a tail up here. So this one is actually, the purpose is to integrate the governing equation into the network. And we also have a boundary condition, of course, if we want to solve the PDE. So that's some like a simulation results and compare with the field measurements. You can see that in general, I mean, this method gives us acceptable simulation accuracy, which is enough for the engineering purpose. More importantly, it's very, very fast. Okay, so we use can use the laptop, probably like in the order of seconds, we can get the whole wind field by using these machine learning tools. So once we have this like a faster calculation model for the wind field, and then we can do a systematic comparison of the simulation results between the current climate and the future climate, or the historical climate and the future climate, more specifically. And then we have simulated a total 10,000 years hurricane events. And so in general, we find that the higher hurricane surface wind speed were obtained for all level of MRI, that's the return periods, and the change of climate based on the selected global climate models. And for example, the wind speed corresponding to a 50 years MRI was projected to on the RCP 8.5 climate scenario to increase around like 15% at the location of New Jersey. So the first question is that does our change climate intensify extreme wind storm? Our simulation indicated the answer probably is yes. And then the second question is, what would be the bridge performance under the intensified wind storms? So to assess the bridge performance and under the intensified wind storms, let's first see a quick example. What would be the performance change? So this is a Shihomen Bridge in China, and in the very early design stage, actually the original design, the box girder is a single box girder, and so then the experiment has been done at Tongji University, and the researchers at Tongji University realized that the flutter critical flat wind speed is too low. Actually, is below the design wind speed. So they kind of change the design and modified it to make it the twin box to increase the flat speed. So this is the wind tunnel. I mean the results. The required design wind speed at that specific location is 80 meters per second, and the single box is 45. And change it to the twin box is 87. So then design is good after the modification, aerodynamic modification. So if we move this bridge, because we didn't do the climate change impact around the China coastline, we did it along the US coastline. So if we move the bridge to the New Jersey, some location, because the climate change impact on the design wind speed has been increased by around 15%. And then you will see that the current critical wind speed for the flutter actually is below to the design wind speed again. And in that case, what will happen, right? Of course, so I mean, we also, on the other hand, we also need to consider the materials deterioration for our structures, right? That part my research group doesn't count for, but the task group 6.1 and you just mentioned, we have just published like 2 papers. So one paper is about the hazard intensification, and the other is about the materials deterioration under the climate change. So with those like climate change on both like the demand side and the capacity side, we don't want to like Takamonaro or like disaster happen again, right? Nobody wanted to see that. So and then we need to first, at least we want to assess what would be the post-Flutter behavior if our climate change do increase the wind speed at the specific locations. So to simulate the bridge performance, again, we can go to the CFD and use the coupling of the CFD and the CSD. That's a finite element model of the bridge deck. And we realized that if we want to get a very accurate the response and the computational cost is really high. That's I guess I think I don't remember exactly, but my students simulate one case. It takes several months, and so we trying to find like a more efficient way. So one way we can do is that we use the so-called like 2D CFD and 3D CSD, so that at each like nodes of the important nodes of the finite element modeling, we have a CFD. But that part is still like time consuming. So this is also why over the probably the last several decades, I mean, the bridge aerodynamics community, we have spent a lot of effort trying to develop all kinds of reduced order models to improve the efficiency to get the aerodynamic load, so that we can get the structural performance assessments. And recently, what we are interested in is that to do the based on the so-called the machine learning tools. So the traditional artificial neural network cannot reliably capture the information, because for the bridge aerodynamics, we have a very special feature is that we have fluid memory effects. But the conventional INN, this actually like probably like 10 years ago, 15 years ago, we did our first like artificial neural network and to capture the aerodynamic load. And it's not that the performance is not that promising. So we kind of stopped the work a little bit, and then after a number of years, and then we have deep learning, we have all kinds of fancy machine learning tools. So one example is the LSTM. So LSTM can capture the fluid memory, and so we used this one, and also on the top of that, we kind of used the so-called non-enhanced LSTM, because we know what was that some like unique features of our system, and so that we can kind of customize the LSTM for us to use to more effective use. So one knowledge actually for us is, for example, we know the bridge the fluid memory or for the bridge aerodynamics, they are decay, right? So we don't need like those kind of very long memory. And so all those kind of knowledge in the domain help us to customize those LSTMs and cells, so making it more efficient, more concise to be used in the simulation. So once we have the LSTM cells for our bridge and the aerodynamics, and then we can couple the LSTM network with the structure model, and then we can get the post-Flutter behavior, the performance of our structure. So you can see it. I mean, if we can, because those LSTM or those kind of network, one feature is that they can consider nonlinear effects, right? So you can see if we consider the nonlinear effects, the post-Flutter behavior is not like the linear analysis go to divergent. And instead, they have a limit cycle oscillation at each wind speed beyond the critical wind speed, and of course the amplitude will increase. So then one observation is that the nonlinear post-Flutter behavior of those this example bridge suggests that it might be beneficial to allow the bridge design wind speed higher than the critical Flutter wind speed. So which means we may not need to do the retrofitting if our bridge post-Flutter behavior is good. And but on the other hand, is that we don't have established a good performance evaluation. For example, the few literature we can identify is like Selberg point out the bridge is able to withstand a torsional vibration amplitude 0.1 rem. But the 0.2 maybe soon will result in catastrophic failure, that collapse. But how to accurately establish the performance objective and how to evaluate the performance? Actually, this is the key to advance the performance-based wind engineering, and especially its application to the bridge design. So in the seismic engineering, I mean, research just around the performance-based seismic bridge design report, and in the wind engineering, we 2 years ago we have the pre-standard for the performance-based wind design, but that pre-standard is specific for the buildings, tall buildings. And there's no single documents or even papers to talk about the performance-based wind design for long-span bridges. So still lots of work to do to kind of reasonably evaluate the performance of our bridges and strong winds. So the second question, I mean, what would be the bridge performance under the intensified windstorms? So the answer might be the limit cycle oscillation. And then can we efficiently produce an optimal design for bridge wind retrofitting? Let's say the limit cycle oscillation amplitude is too large, and we don't want to happen. Or some they may don't want to post-Flutter. Right. So then how can we retrofitting efficiently? So to get efficient retrofitting, then we need to build the gap between the kind of traditional segmented approach for the design process. And then a seamless bridge is needed between the engineering design and the stakeholder for decision making. So in the wind design, the one key is to get the aerodynamic load, right? So then we kind of borrow the concept from the actually automotive industry. That's the interactive aerodynamic design. So the concept is that if you give a shape, or that's the geometry of our bridge, and then the tool will give you the aerodynamic load. So to this point, I mean, then we proposed the end-to-end pixel-to-pixel flow pressure field simulation used the non-enhanced CNN. That's the convolutional neural network. So the idea is that if you give us a bridge shape, and then we will kind of almost immediately give you the pressure field and also the velocity field surrounding your bridge. So all those information output can be used for the wind design, not only structure design, but also wind environment consideration, because we also get the velocity field surrounding the bridge. So currently we have done this bridge. The shape design used these tools, and then but in 2D. So we are kind of use the knowledge enhanced system. And what that means? That means we have integrated, the quantitative knowledge and also the equation free knowledge, and also the most importantly is the equation based knowledge. That's the Navier-Stokes equation in terms of mass and momentum conservation. We embed those knowledge into the convolution neural network. And currently, what we are focusing, we were trying to extend from the 2D to 3D. That involves lots of data to processing, and so the process is a little bit slow. But based on the 2D's performance of this tool, it seems very promising to achieve that eventually 3D and help us to get the practical applications. So if the optimization or retrofitting option is not that satisfactory, then we can even need to go to the control part. So we can use the deeper reinforcement learning to do the VIV control, buffering control, all those control things. But this part, it's just some numeric example demonstrate. The AI can help us to do the control very effectively. Whether it can be really implemented, that's probably a long story. It's always about it's challenging, right, to install any control things on the bridge, especially if we want to do the active control. So the third question, can we efficiently produce the optimal design for bridge when the retrofitting? Our answer is yes, and the approach is use the interactive aerodynamic design, and we can develop all kinds of AI tools to achieve this goal. So the last question is that can we validate, because either the bridge performance, post-Flutter performance, and the intensified windstorm, or the optimization, shape optimization, all those things actually is in the numerical world, and also it's challenging to validate through the field measurements, right? So most of the cases we do the wind tunnel test to validate this, all those kind of simulations. But if our bridge go to the nonlinear, right? So the wind tunnel, let's say we have this giant bridge. This is a 3-tower bridge, and this is Tongji University. They have a big wind tunnel. They do the test, right? They can try to reproduce those bridge behavior. This is the collaborator, I think, Professor Min Zhao, trying to stop the flutter, right? Once flutter happened, that's very, very scared. And so the in the wind tunnel, I think one issue is that the Leno-Slumber effects. That part, people spend a lot of effort trying to identify or trying to kind of understand what is Leno-Slumber effects. And we to capture those especially during the transient wind at the University of Buffalo, we also build a wind tunnel. The purpose is to kind of generate those kind of transient wind, so that it can help us to more accurately simulate the wind flow. So see, there have been over the last several decades, actually, in the wind tunnel, people's focus is on the more accurate simulation of the wind flows. But on the other side, our structure, you see, it's very small. It's kind of like a tiny toy, right? In the wind tunnel, because the length scale is usually 1 to 100, even 1 to 200, right? And then we have in the wind tunnel, so actually it's not easy to consider the structure behavior, especially if our structure go to nonlinear domain, right? So how do you consider that, right? Because, for example, for the current 4-bridge area elastic model, we probably can consider the first several modes. That's it, right? And you can imagine that if for those kind of small scale it's very difficult, challenging to fabricate and model so that it can reproduce the structure behavior of the real world, right? So to consider this challenging, we kind of think, okay, maybe that because the structure analysis, is already, well developed. We can say, right? For example, for the to capture the global behavior, or even to count the geometrical nonlinearity. So we have all kind of a good algorithm to help us to capture the structure behavior, right? On the other hand, the aerodynamic behavior is represented by the shape of the bridge. Actually, it's the most reliable way is still in the wind tunnel. So we have been thinking whether we can combine these two worlds. One is the aerodynamic capture in the wind tunnel, in the physical world, and the other is the structure dynamics behavior capture in the numerical world in the computer. Okay. So, but because of the aeroelastic effects and the real world change will impact the virtual world change immediately, right? Then we need to do the real time combination, right? So this is interaction between those skeleton represented the structure dynamics and the skin represented the aerodynamics. They are accomplished through a system consists of sensors, actuators, controllers. So actually is the real-time hybrid simulation concept. So because in the wind domain, we can say we call it real-time aerodynamics hybrid simulation. And so we have did some tests for use the bridge deck to do it's kind of a digit twin in the wind engineering. And then we installed bridge deck, and then we use the electromagnetic actuator to do the to control the physical bridge deck in the wind tunnel. Of course, this is a big field in the control algorithm because for the real-time hybrid simulation, and because all kind of time lag is inevitable, and we kind of actually is my collaborator and seismic engineering. We developed the novel control design so that ensure the accurate and actually present the virtual skeleton model, which means we get rid of those structural control interaction, and also we deal with those the time lag because of the calculation and because of actuator dynamics, all those kind of things. Okay, so another thing is that even though our structural behavior can be captured accurately by the structure analysis model, it takes time, right? For example, for a giant like FEM, it will take time to calculate. And on the other side, the real-time hybrid simulation, we have a very strict requirement for the time lag, right? So we need to make the calculation very, very fast. So what we do is that we generate some data using like a high fidelity FEM model, and we build another network. So that's the based on the recurrent neural network. The reason we call it also again the knowledge enhanced neural network is because we also in this network we have integrated the equation of motion. That is the governing equation for the structure dynamics, right? That we integrate the equation of motion into the network construction, and so that it can be more efficient and more reliable when they predicted the structural dynamic response. So the last question, our kind of initial step is to say maybe the real-time aerodynamics hybrid simulation can help us to validate the simulated wind-induced nonlinear bridge behavior in the wind tunnel. So with that, I think that's all for my presentation, and thank you everyone, and I welcome any questions from the audience.
Thank you, Tang, for your very interesting presentation. I remind to the audience, you can put your questions in the QA, and I will address them to Teng.
Thanks, Angel. So, oh, sorry, I forgot to mention, and we can't all those work and relate to two committee, and I encourage everyone, I mean, if you are interested to join the committee, sorry, I asked, I mean, this committee is from ASCE, and if you're interested, you'll become the member, you can enjoy the climate change committee and also Cape Support Bridge committee. Thank you.
Thanks, Teng. Can you come back to the slide where you show all the questions? Or maybe it was the slide 22, or when we see all the questions you address in the presentation. Does our changing climate...
this one?
Yes, this one, exactly. So it's very interesting. You try to address very different fields of this topic of changing climate. Do we experience intensify extreme windstorms, until how the structure is behaving under this changing climate. Considering, and maybe in this Q&A session, I think it would be good for the audience to see these questions, and maybe they will have some, some questions to know how, more in detail, how you consider all these aspects. Maybe a first one, for the first question, and you develop an advanced risk framework that you show some of the results in the northeast side of the US. If I wanted to apply some similar approach in a completely different area of the world, how much data would I need to consider a similar approach? I mean, I guess you need so much information for this risk framework. What is your opinion? Is it something that you can manage easily, or considering the volume of information, of input information that you need from environmental parameters?
Yes, I think that's you are right. That needs lots of data and to input to this kind of a model. And I would say similar approach have been developed over the other part of the world. And even in US, so, I mean, we have several groups, I mean, in addition to my group, to develop this type of work. And the challenge here is that the input we get is from the, let's say, global circulation model or global climate model. But nowadays we have plenty of those models. If you run different model, you may get different results. I think that's the challenge part. And then if once we get the input from the global climate model, and because as you are clearly point out, because we are doing the risk in sense, right? Then our model needs to be run many times. So this is why, I mean, we propose use the kind of surrogate model or AI tools to help us to speed up, to facilitate the simulation. So once you build this kind of AI models, and for any you kind of do the Monte Carlo simulation, and then you can very fast to get the wind field. That's the output for our purpose. So I'm not sure whether I answered your question.
Yeah. We have a comment from David Goodyear, a comment and a question. So first a comment. Performance-based wind design has been standard in long-span wind design for over 40 years, based on local wind climate studies on wind tunnel models. And the question is, what calibration have you performed for your climate model, given that in the Gulf, the accepted maximum wind speed is still from Glaveston in 1900? What calibration have you performed?
Yeah. Okay, let me. So I can actually see, thanks, Andrew. I can see the question. So okay. For the comments, I appreciate these comments. But the performance-based window design, I think there is kind of a different concept about the performance-based window design. So the first thing for the performance-based window design for the let's say currently people trying to advance in the tall building is to make the structure go to the nonlinear domain. That's one advancement we're trying to pursue, and that caused lots of issues because of low cycle fatigue and because of the material deterioration in the inelastic range. And I'm not aware of like a performance-based window design for the bridges because I'm not aware of all those kind of consideration for the low cycle fatigue and what is the performance objective specifically go beyond the linear analysis. But if I'm missing that information, I really appreciate it if I mean the David Gordiers can share this to the others, because there are a number of people and in the committee and of cable supported bridges, I mean, they are interested in these aspects and where lack of information. So to the question is that the climate model, in generally for the hurricane and the climate change impact on the hurricane winds and on the design wind speed, we have been validated by the historical data, because around the US and we have let's say the way we to validate is two approach, two steps. Step one is that we use the current climate or historical climate and we run the model. And then we compare it with ASC 7, the wind speed, design wind speed. That match means, okay, at least our model is okay. And then the second part is that we use the input from the global climate model, and then we get the results. That part we cannot validate, and because that's the future, right? We don't have the data to validate. But if we validate it based on the ASC 7 when design wind speed map, and then we assume the model developed is reliable.
Okay. When you present your results, you showed some results with the 8.5 RCP. Do you see different conclusions when you apply different scenarios, RCP or SSP scenarios?
You mean the different scenario, right?
Yeah, yeah.
No. For us, we did some work. We tried because when we did the work, the SSP is not has not been issued yet. So we used the RCP. We tried RCP the 8.5, and we also tried RCP, I think at the middle level. But we just tried that, and I don't think that because as we said, I mean the IPCC, when they issue those scenarios, they don't kind of match. Kind of what's the probabilistic, right? What's the probability of those emission scenarios? So we have no idea. So it's just my current understanding is kind of a user selection, right? You select your own emission scenario. So that's and of course, if you select, most of us, I mean, trying to do research, we always select the worst case, right? And to show the big difference. But I mean, in addition to that part, we didn't do much work on that about those kind of systematic comparison about the different scenarios.
Okay. I see that there is a comment from David. The question then remains whether the IPCC models are valid given the hurricane history in the Gulf. So maybe if you want to further discuss this point.
the IPCC models are validated given the hurricane history in the I think this one is, I mean, to my knowledge, I didn't do this part. To my knowledge, that people have done those kind of work, trying to use the like historical data and the current data. They are trying to compare. They do realize that the climate change effect based on the IPCC's model, and they matched some observations. But the thing is that I mean the comparison is not that straightforward, because we are talking about the I mean is about the statistic, right? So we can, if we are doing like kind of many people do the like a hinder cost, right? Of the so let's say we have a hurricane, we are trying to check whether, I mean, this is from the climate change, and that part people have done. I mean, the hinder cost and of a hurricane, and to say the climate attribute. But in general, and the confidence to doing those kind of validation, I mean, as I showed in the first, almost the first slides, is that the National Academy, they have done those kind of research, and they show the confidence of IPCC models is well, between low and high for the hurricane. So it's not like the let me pull up. I still show the screen, right?
Yes.
So I think I don't need to see is this part, right? So there's low confidence, high confidence, and so for the extreme heat cold, there's always there, but for the tropical cyclone, we're kind of in the middle. It's better than the like non-solicited wind, downburst, tornado, but definitely needs to improve.
And Tang, do you try in your research to have some kind of holistic approach in which you look at the changes in the load part, as you presented here, but also on the change on the considering additional structural deterioration, so on the resistance part, to try to combine both?
That's the plan. We didn't do that yet. We noted some work, I mean, very nice work, and we're trying to also go to that direction. But the short answer is we didn't do yet. But we noted that part. More specifically, I guess, I mean, during the preparation of that paper, right? The task group paper. And actually the deterioration, that's very interesting part, is not only they change the stiffer and all those things, they actually, if we consider dynamic property, that's probably even interesting to have a look, because the wind and, for example, the flood, they depends on those kind of properties.
Yeah. And in your calculation, do you observe results that would not seem obvious, that come directly from your conclusions, that you know would not seem obvious at first glance?
Pardon me, could you say again?
Do you obtain, do you draw conclusions that would not appear obvious at the beginning, after the calculation process? You obtain some new types of conclusions regarding the behavior of
you mean the bridge behavior, right?
Yes.
Yes, I think thanks for this comments. I think that's the behavior of the, let's say we go to the post-Flutter range. All those behaviors, in a sense, it's not that I mean accurately reflect the truth. That's because, as again, I mean, it's very difficult to get a conclusion about the bridge performance is because we don't have the performance objective set up. And this is actually also the reason we have been believing that the so-called performance-based wind design in the bridge domain actually has not been systematically established, because we don't even have a, let's say, a metrics to help us to evaluate the performance. Think about this, when we design the bridge and when we hit the flutter speed, right? Then we say, okay, let's change the shape of the bridge, do some like the modification. Then we'll make sure flutter will not happen. And even now, if we make the flutter happen, and then what would be the good amplitude we allow to do the limit cycle oscillation, right? Is 5 degrees of freedom, is that acceptable? How many hours of 5 degree limit cycle of oscillation the bridge can resist, right? We have a big storm, we have and then if we have 10 degrees of freedom, 10 degrees of vibration, what is the behavior of the bridge? How long it will resist? And what would be the first parts of our bridge under the extreme storms to have some damage, right? What's the low cycle fatigue behavior of those important components? All those things, I mean, to me, at least, I don't know the answer. So I think this is very challenging to evaluate. That's the reason, in my opinion.
Yeah, very challenging. Maybe one question regarding the machine learning and the LSTM network. You more or less simplify or enhance the architecture of this LSTM cell. And you mentioned general knowledge, domain knowledge. Can you further explain what is behind this step, which I think is essential so that you reduce the needed to train the network, but in parallel, you have something which is adapted to your problem?
Yes, I think the whole idea is that in engineering, and when we're trying to adopt like machine learning, I mean, nowadays there's so many fancy tools for us to use, right? And they're always, I mean, our thinking is we never used a tool we don't understand. So that's the black box, right? We have input, output, we have no confidence on that. So the first part is we want to understand how that kind of tool machine work. So once we understand that what's the information flow about it in the original LSTM cells, and then we understand what's the behavior we wanted to reproduce, and then we realized that okay, there are many like kind of information flow. They are kind of do the same thing. And then we said, okay, maybe we can combine several of them. That is based on the general knowledge motivated by mathematical model of information processing. So we have input, we have output, but the input is not, because the LSTM is designed for the speech recognition. And the feature, the unique feature of their signal and the feature of our signal, they are different. Our signal is the input is the motion of structure, and the output would be the aerodynamic force. So we actually first the so-called general knowledge actually is something we tried many times, and then we realized that those information processing, and then we combine several of them. The domain knowledge is about LSTM is trying to recognize or remember what people have said, have speak out, and so to recognize the speech and all those kind of similar things. That's the original design of LSTM. And then for us, and we actually the aerodynamic force depends on the input, the motion, but it also depends on the history. But think about it, if we have a history of the historical motion, will not forever impact the aerodynamic force. So its impact will decay. So those kind of decay will help us if we do, for example, if we have a flat plate, we have a Kushner function, theoretical function to guide us. What will be the duration, memory effects duration is reasonable. So based on all those kind of aerodynamics knowledge, we can further simplify the cell, the LSTM cell. So that is kind of this process. I'm not sure whether I answered your question.
Yes. And so here for this case study, you have specific and advanced modeling. Do you have a plan or do you have a strategy to try to translate this advanced modeling into some conclusions that can be manageable for practitioners? I don't know, considering recommendations after having applied this type of methodologies. I don't know, considering design wind speeds to consider or critical flutter speeds. You try to go until the stage of recommendations for different families or different types of bridges?
We don't have that part. I mean, currently we are trying to cooperate with others and several groups trying to identify. So here is the situation. So it's just my personal opinion is that the climate change impact. I mean, you can choose to believe, but some people choose not believe. Right? I mean, that depends because, I mean, that's the future. I mean, I choose to believe. So I will see there will be a risk and there will be wind will be intensified. But then again, this is for the future projection and with lots of uncertainty, how we're going to handle that. So what we are trying to do is that we identify those locations. We're trying to identify those locations with those wind-sensitive bridges. We're trying to get the information of those bridges information and the design wind speed and the flood speed. We're trying to compare. We're trying to do those kind of work. We're trying to get people's attention. At least we may have those kind of situation to say that because of the intensified hurricane, maybe the bridge already built, their risk has been increased. I mean, the tool is here. If you want to do the retrofitting, and people can do that, right? Nowadays, I mean, people can use all kind of, even purely rely on wind tunnel, they can do the retrofitting. They can add something like to make the bridge more stronger. But I think here the obstacle is like what kind of attitude the people select to choose to believe this or not.
Mm-hmm. And currently, so the research needs or the research, yes, the research needs you identify at this date, maybe considering what could be improved in your modeling or what still need to be looked at in this field.
I appreciate this this question. I think that one way is that people to select whether they will believe or not. The other way is that as a research group, I think we need to do something to enhance or to kind of let people to deliver the results so that people can be easy to understand, and so that they are more being convinced to believe the result or to accept the results. So one way I think we can do is doing the kind of risk-informed decision making. So we wanted to admit the decision making is under uncertainty environment, and we deliver the result with the risk-informed the results. so that people will have a sense, right? It's not a perfect deterministic way. It's a risk-informed way, and you want to make a decision, and then you have to get used to the risk-informed decision making. And plus, as we said, the emission scenario, there's no probability there, right? We may need to, and also we don't know how much like there's no, I mean, the holistic like research tells what's the uncertainty like qualification, like I mean like the previous question. I mean, there's all kind of questions about what's the simulation high fidelity, what's the like uncertainty qualification. Then what we need to do is we need to design I mean, many people, I also prefer the dynamic climate adaptation, which means, I mean, we don't want to like retrofitting something, like spend a lot of time and effort, and then we regret, right? We say, hey, the climate change is not it's not happening. We spend so much effort and money. We don't want to do that, right? We want to do dynamic adaptation, which means we want to do something based on observation, and then after 20 years, based on observation, we add on something, and with low cost, right? We want to do like, we don't want to do one-time invest and then to say regret and why this like simulation, why this projection is not that accurate. So in some field, they have a so-called observational method. This is kind of related to the dynamic adaptation, like the climate adaptation.
Then we have a question of Sang Boom Kim. Regarding the intensifying windstorm case, considering the approaching windstorm seems like generate lower response if the max wind speed is same, because the conventional simulation assumes that the aerodynamic forces act simultaneously. Would you like to address this comment?
I think the conventional simulation also assume aerodynamic force not simultaneously acting on that. Because the conventional way to consider the aerodynamic force, let's say if here the aerodynamic force is the like constant buffeting, I think that we always consider the correlation, spatial correlation in the around the structure. So I mean, maybe some like design, like they just for the conservative consideration, they have assume simultaneously, I mean, the aerodynamic force, but actually there is, I mean, well-established like framework to consider those correlation among those kind of locations on the bridge in space.
Okay. There is another question from David Goodyear. Are you extending your work to non-hurricane climates in AA? There are some climate studies for wind power showing that mean wind speeds go down for some latitudes and up for others. These studies generally deal with means rather than extremes, which is a good question. So it may be instructive to look at your models for bridges not exposed to hurricanes.
Yes, I think this is a very good question. This is some, I mean, I encourage people to join our climate change committee, because we're trying to do this work, but we're not yet. We're still in the beginning stage. It's not my work. I mean, it's a group of fantastic people and getting together. We're trying to see, yes, you are right. I mean, the mean wind speed for many locations, they are getting lower. That is bad news for the wind energy community. But for the wind extreme, and we also not, first, the work I presented here only for hurricane, because we have a hurricane model. So it cannot be straightforward to move to other storms. For other storms, the framework, I mean, the methodology can be similar, can be used, but there will be lots of effort to develop all kinds of models for that specific storms. And also, it's more challenging. So we get some research, they're working on the tornado, climate change on the tornado, climate change on the downburst. And all those work, I mean, I said again, back to that chart. I mean, the confidence, prediction confidence is very, very low. That's probably the lowest. I mean, for the climate change on the hazards is the non-slippery winds. So that part needs lots of research, and our research has not been extended to that part. But it will be interesting to see among the different MRI, let's say MRI to like 10 years, which means kind of normal wind, right? Mean wind, and then to 3,000 years. Along the MRI, what would be the climate change impact on the change of the wind speed corresponding to different MRI? That's something we are very interested in, and we are looking for.
Then there is a question from Rohan Eshag, considering the LSTM network calibration. How do you deal with the non-stationary aspect of the extreme climate events in your LSTM network calibration?
I think there's two separate issues in my understanding. So the non-stationary aspects of the climate is a little bit different with the non-stationary winds we are talking here. The non-stationary aspects of the extreme climate is because our climate is changing, so we cannot treat it as a stationary way. So that, for example, even the MRI, the conventional time period, they are not that promising or that valid anymore because of we have a changing climate. That's the non-stationary part. That's no relevant with the LSTM network calibration, because our LSTM network is given wind condition and then to capture the aerodynamic loading, so that the calibration of LSTM can be separated from the non-stationary constellation of the climate.
Okay. Maybe one more last question, if there is in the audience. No questions anymore. Oh, yes. No. Okay, that makes sense. So it seems our time is up. I would like to thank you once more, Tang, for your very interesting presentation on a very challenging topic. For the audience, if you're interested by this topic, do not hesitate to contact Tang or even myself or the IAPSE secretary if you want to join the work that is performed in our task group or in more general by the IAPSE community. Do not hesitate to send an email and to try to, yes, see what we can do together. I thank you all for attending to this webinar today. And yes, with that, we will conclude this webinar. Thank you all. Have a great weekend, and bye-bye.
Thanks, Angel. Thanks, everyone. Bye-bye. Have a nice weekend.
Bye.